Welcome back. In this video, we will continue our discussion on data preparation. We will cover missing data, an important topic requiring some serious thought. The first question we need to ask is, do we know if any data is missing? That may not be an easy question to answer. Suppose you have a data set with 5,000 observations. How do you know that there weren't 6,000 observations and only 5,000 were shared with you? One way to answer this question may be to just ask the data provider or use your domain expertise to question the completeness of the data. For example, if you are expecting data on all 50 states in the United States and your data has only 43 states in it, you have to think about what happened to the data for the remaining 7 states. Maybe those states did not have any data to report in the first place, but you need to make sure that that indeed is the case. Once you know that you have rows or observations missing, you need to find out why the data is missing. If each state in your dataset is missing rows at random, that may still be okay. But if the data is missing in some systematic way, for example, if all the states on the east coast of the United States were missing from your data, then you have a bias introduced into your dataset that will affect your conclusions. Think about if you can reacquire the data, and if not, is the data even usable anymore? A more common situation is where data is missing values for just some of the fields. And this could be because of any number of reasons. For example, there was an error made in data capture. Maybe a particular sensor that was responsible for collecting the data lost power briefly, some server went down, so some data was lost, etc. So this incidentally would be the kind of situation that we can apply some techniques to address and still be able to use our data set in spite of missing values. With that, let's switch to the slides and let's look at some content. As I described, when you have entire rows of data missing, you have to think about how you will use the rest of the data set. And it is possible that the rest of the data may not be usable unless that problem is addressed. And the second situation is, so consider this randomly generated data set, and the red items are the missing values. In Python, which is where this particular graphic comes from, missing values can be represented as NaNs, or not a number, or none, or nulls. And this is what alerts us to the fact that there are some missing values here. So we can do a number of things to address these missing values. We can ignore all the rows that have missing values. But if we do that, we find that we are not really left with much. So that is a problem. The second is we could replace this missing values with something else. Or we can be a little more scientific and use some machine learning or other approach to calculate and impute the value. And we will look at all of these things in a little bit of detail next. So one other thing I wanted to mention was that very often missing values in your data may not be obvious. They may appear coded in different ways, for example, as -1, 999, or just the letter M, or missing, or zeros, or dashes, or something else. For example, NA is also something I have seen. So you have to figure out what represents missing data in your data set and be able to understand the scale of the problem. So that's one thing I wanted to mention. And once you know what represents missing data, then it is reasonably easy to get counts or an understanding of the proportion of the data that is missing, whether by features or columns or by observations or rows. When some values in the data are missing, you can drop or delete the rows that have the missing value. So in this situation, for example, if this row is missing a value, we could just ignore it. We just have to make sure that we don't introduce any systematic bias into our data as a result of doing such deletions. We can also approach the problem the other way, which means we could look at columns that are missing values and we could drop those. Here we would end up dropping the first 3 columns because they have missing values, but we will keep the rest of them. Now this may look very drastic. And one might say, is the data even usable after this? But in practice, when you have a data set with several hundred columns, and many of the columns do not have any values, then if out of 300 columns you drop 40 or 50 that don't contain much data anyway, your data set may still be quite usable and contain good information and provide you with good analytics. The next option that we have is we can replace the missing values with a static default. So for example, if we are missing state, then we could replace the value of the state with uh, the state that is the most common in our data set. If it is a numerical column, we could replace missing values with the mean or the median for that column. And finally, we could apply some machine learning or other techniques to impute values for our missing values in a more sophisticated way as well. So now let's look at a little bit more uh, for what we can do for each of these options. So first, as we discussed, we can drop the rows with the missing values. Generally, your analytical software will give you several options which you can use for your deletions. You could set a threshold. So you could say that a row or a column should be missing at least 2 or 3 or 5 or some threshold number of values before that row is deleted. So that can help you delete only the rows that have the most egregious number of missing values. And you can apply other conditions as well. The next approach is to drop the columns with missing values, and we covered that a little bit earlier, so I'm not going to repeat myself here. The next approach is to replace missing values with some data. The problem with deleting rows or columns for the sake of 1 or 2 missing values for an observation or for a column is that you end up throwing out a lot of other good information or data that you don't want to lose. If the data is not missing at random, then you might be able to replace the missing values with some other estimate. For example, the mean, the median, or in the case of categorical variables, you might be able to replace it with the most frequent value. And that generally is a pretty good approach that works reasonably well. We can also replace all missing values with a constant that we specify. Sometimes missing values may appear in multiple columns, so you may have to be careful about using a different constant for each column. For time series data, we might like to use forward fill or backward fill. This is an interesting approach, and let me illustrate this with an example. Forward fill is also called Last Observation Carried Forward, or LOCF. This is the acronym you might encounter in the data world. In forward fill, what you do is you take the last known valid value and you copy it forward wherever you find a null or a missing value. And backward fill works exactly the opposite way. So here, for example, we have some time series data relating to the sales for actually this is from a toy data set, and it lists the wine sales of independent winemakers in Australia. So here we find that we have these missing values. And the way we fill it is because we don't know the value for March 1980, we assume that this must be the same as the previous known good value. So we copy the same value here that we had for the previous month. We do the same thing in May. We copy this value here. So we are basically just taking the last known good value and copying it forward. And we will copy the same 177 here and so on. And here is the result of the forward fill. So March gets the value for February and so on. And we now have a complete data set. You will notice we still don't have this value because there was nothing before January 1980 in our data. For this one, we could use backward fill, which means we could ask it to populate it with the value that came after. And once we do backward fill, we find that we have a complete time series, and we can graph it, we can do additional analysis on it, and so on. Because we did the backward fill, these got dropped out. And what we also find is that these values are different because this was created from the forward fill and this was created from the backward fill. Finally, the most sophisticated approach to missing values is to impute the missing values. So really, what we do is we use some regression or some machine learning or other algorithm to calculate what the missing values might be, what would be the best estimate for the missing value, and use that to complete our data set. You can pause the slide and you can read all of this text, which is from scikit-learn, which is a library used in Python for a lot of scientific and numerical work and for machine learning. But I will not read through it. Let's just look at an example which makes it a little bit more real. Similar to Python, the R ecosystem has several libraries that implement imputation mechanisms. One of the more interesting ones is called MICE, or multiple imputation using chained equations. And let's look at an example. And this example is from the CRAN, from the R project's website. So here we have a situation where all the values in red are missing, and we have three columns, A, B, and C. What we do in this situation is we use two of the columns, in fact, all the columns except the one that we are trying to estimate, and use these to estimate the value in the first column. So we use regression or something else to calculate a value here. Now, obviously, this is going to be an estimate. But once we have done this, we will use this column and this column to calculate the next one. And then in a similar way, we will calculate the third column using the values, including the imputed values from the other columns, and fill up this one as well. Once we have done that, we will repeat this process several times, which means we will keep going back and forth till the values here in all of the missing cells start converging. And that gives us our best estimate of missing values and allows us to complete our data set. Obviously, this approach is not perfect. However, it gives us results which are much better than replacing missing values with constants or with measures of descriptive statistics like mean or median. But this approach can be quite effective for some data sets. A similar approach is called predictive mean matching. And what we do here is that if we have missing values, for example, if we are trying to estimate the values here for missing values for column A here, we will make an estimate of every single value in this column using the values of B and C and keep it in a separate column. Then for these estimates, we will find out the value closest to the one predicted for the missing cell. So for this particular cell, we have an estimate of 0.60, and another cell that has a estimate closest to it, 0.62, is the second observation here, which carries a value for A of 0.24. So we will use the value of 0.24 for this particular cell. And we continue this way and finally get to an estimate of all of our missing values. Which of these approaches is better? The MICE approach or predictive mean matching, again, depends upon your data set and depends upon the results that you get. And here is an example of the same approach being applied to a toy data set. So remember our cars data set where we have data on a certain number of cars from the 70s. And what we do here is that we take our original data set. Let me change in color to something more prominent. So we have this original data set, and at random, we remove some of these values. So for example, we replace many of these values with a blank. And we do this at random. What we are going to try to do is to do an experiment. We will ask the algorithm to calculate the values that are missing in this new revised data set. And once that estimate has been made, we will try to compare it to the ones that we already knew are the correct values. So that is the experiment we will try to do next. And we do that using the iterative imputer, which uses an approach very similar to the mice approach that we saw a little bit earlier. And here are the results that we get. And we find we are actually pretty close. So we get a 1 here. Let me change in color. Whereas the estimate is 0.7. Similarly, the estimate is 4.5. The actual value was 4, which is not so bad. We get 5.2 as the number of cylinders. The actual number of cylinders was 6. So it is getting us pretty close. It's not exact, but it is getting us pretty close. Yet another approach is the nearest neighbors approach. What that means is that if I'm looking for missing values for a particular observation, perhaps the best way to do that is to look for other observations that are very similar to it, or are exactly like it, or in some ways, mathematically, are its neighbors, and see what values they have for that particular missing cell or missing value. And we can do that calculation algorithmically using available libraries in Python. When we do that, it looks like we get better results. So this time, the machine is able to calculate the number of cylinders correctly. So things are much closer. But again, which of these approaches is best is something you will need to decide based upon your use case and the results that you desire. If you are building a model, then whichever approach gives you better evaluation results, that's probably the one to go for. So a lot of this work is going to require trial and error and experimentation. But there are solutions to addressing the problem of missing values that we as analytical people should be aware of. With that, we will end this video. Thank you for watching, and I will see you in the next video